Thanks a lot, Vijay, for the introduction, and thanks everyone for staying up to this last talk. So the purpose of this talk is to provide two online platforms where basically exhibit high levels of externalities. By externalities, I'm referring to the effects that different agents have on each other as a result of different resource allocation strategies. So the two problems that I'm going to describe today, they are actually some online version of some of the classic problems which has been studied widely in the past literature. And one is related to the data placement problem, which I will explain soon. The other one is related to online assortment, which Rod and others discussed about it before. And I'll provide some algorithmic results as well as complexity results on how far we can try to get optimal solutions or get good competitive algorithms over there. Okay? So the first problem that I'm going to jump in is, for short, I call it online resource allocation. And here is two brief motivating examples. So suppose you have a network of servers where each server has limited cache size. So it can cache only a limited amount of data. And when clients come to these servers and request for some data, either you have the data in the cache, which you simply provide to the client, or you have to request that data from the closest server, which has that data in its cache. Okay, and that requires some delay costs, incurs some delay costs. And the question for the platform is how to distribute the data in the cache of the servers in order to minimize the total delay cost. Okay? A similar example happens in product distribution network. So here you have a bunch of local centers, let's say, and they have limited inventory storage levels. And you want to store the items in the local centers such that when a customer comes and requests for that item, either you have the item in the inventory which you provide to the customer, otherwise it has to be shipped from the nearest local center to the current local center, and that requires, it incurs basically some shipping costs. And again, the goal is to distribute the items in the local centers in order to minimize the overall shipping cost. Okay? So these are, you can also think about the online version of these problems. By that, I mean that when new servers are going to join to the network, and you have to decide how to fill their cache. Or when you are going to open a new local center, your question is how to, what items to store in the inventory of that local center to minimize the overall shipping cost. Okay? So moreover, if you look at the second example, here you can assume that the access cost satisfies some metric property because the local centers are in a Euclidean space and in two-dimensional Euclidean space, and therefore they satisfy some metric property, while in the first example, not necessarily the access cost satisfies some metric property because it depends on what is the compatibility of the servers together, and that defines the access cost, and that can be any arbitrary way. So for this example, I refer to the access cost as metric access cost. For the second one, non-metric access cost. Okay. Great. So without further ado, let me jump into the problem formulation. We are going to consider an online platform and with K supplier. Each supplier has unlimited number of one resource type. And we assume that we have in total K resource types. And there are N agents which are going to sequentially join the platform in an online fashion. So we assume that agent I, when it comes to the platform, has a limited cache size of UI. It can only cache UI resource types. And moreover, we want each agent to get access to all the resources. That can be done either by caching that resource or getting access to that resource through another agent which has that resource in its cache. Right? And we denote the access cost between agent I and agent J by Cij, which is a non-negative real number. So as I said, agents are going to come to the platform sequentially over time. And the goal of the online platform is to irrevocably decide how to fill the cache of the new agent which is arriving to the system. Okay, so here is one simple example. Suppose we have three resource types, red, blue, and black. Then the first agent comes to the system. It says I have a cache size of 1. The platform is going to assign the read resource to that. Then the next agent comes. It has a cache size of 2. It reveals its distance or its access cost to the previous agent. And the platform is going to fill its cache by blue and black. And the next agent comes, says I have a cache size of 1. It reveals its distance with the previous 2 agents. And the platform assigns it to the read resource, and so on and so forth. So the question is, when new agents are joining to the platform, how to fill their caches with different resources in order to minimize the overall access cost. So here, there is a strong externality between these agents, because depending on how the platform is allocating the previously joining agents, the new agent is going to get a different types of resources. Okay? Yes, so we are assuming that each agent needs to get access to all the resources. It's big. Sorry?
Like the first agent that arrives here only have access to the demand number, so it should fulfill the demand.
Right. So for example, this agent, which is coming to the platform, for example, it already has access to these 2 resources, but it doesn't have access to the read resource, and it has to go and get it from this agent, right? So it has to travel at least this distance, C21. So its overall cost is going to be 0 plus 0 plus C2.
What about
the first guy? We skip the first guy. The first guy, we assume that if there is only one agent in the system, we just assume that we can give access to all the resources of that agent. That's the exception case. Okay.
What happens if agent 2 has a demand of 1? I mean, capacity of only 1?
Agent 2?
Yeah.
Yeah. So again, in that case, the third agent, we assume that these 2 agents, we need to at least have enough cache memory to make sure that all the resources, there's at least one copy of each resource in the network. And then after that, the platform is going to be strategic on how to allocate the resources. Exactly, the social cost. Yeah. Great. So, yes.
another agent who bought a resource? Is there like a buying cost also?
Good question. So here we are assuming that the buying cost is uniform for all the agents. In this case, we are assuming it is 0. So we just want to make sure there is a local copy of that resource in the old agents. But yeah, I'll get to that question, which is a harder problem later, when we have installment costs for that. Okay. Great. So there is actually the problem that I just described has a large connection with a larger literature on data placement problem, which has been studied by Baev, Swami, and many others in the past. So what I described is a homogeneous online version of data placement problem, which has been studied from the approximation algorithm's point of view. People have been trying to come up with good approximation algorithms to find suboptimal solution in the offline setting. And as far as I know, the best approximation factor for the problem is, I think, 7.1 something. Okay? And this problem is also closely related to classical facility location problem, where, again, in the offline setting, you want to open a set of centers and assign the clients to these centers in order to minimize the total access cost. In fact, this problem is, in some sense, harder because one can show that if you relax the cache constraints, then the problem is going to be decomposed to several resource facility location problems, one for each resource type. Okay? Great. So
Is it especially for metrical task system? The generalization of the facility location?
Probably, yes, it can be cast as net problem. Great, yeah. Good. So the the metric that we are going to use here is, again, competitive ratio, which is the cost of the online algorithm that we are going to design divided by the cost of the optimal offline solution, which basically knows all the cache sizes and the access cost a priori. Okay? Great. So before I get into the algorithmic results, let me talk about some impossibility results that we get here. If you look at the offline version of the problem, where all these access costs are given and all the cache sizes are given a priori, then even in the case of metric access cost, this problem cannot be approximated better than factor 1.001. It is NP hard to approximate the problem. And if you go to non-metric access cost, the problem becomes even harder. It's hard to approximate it within a log n factor, where n is the total number of agents in the system. Okay? Right. So here, for the case of k equal to 2, there is a polynomial time algorithms for this problem, for the top one. Right. So it's important to go beyond 2 resources. Yeah. Okay. But now, despite these impossibility results, we are still interested in finding some good online or offline algorithms to find some good optimal or suboptimal solutions. Okay. And here is what we can show for the case of the metric access cost. So if you consider the problem that I just described and assume that the access costs satisfy metric property, then there's a simple greedy tree competitive algorithm for that problem, which runs linearly in terms of the number of resources and quadratically in terms of the total number of the total cache size of all the agents. So basically, if each agent has a cache of size 1, it's going to be k n squared, when n squared n is the number of agents. Okay? And this is a deterministic algorithm. Well, just to give an overview of how we can show this result is that let's look at this simple example, which is the offline version of the problem. So I'm assuming that each agent has a cache of size 1. And I am assuming that the access costs are induced by the graphical distances here. So for example, the cost of getting access from agent Y to the black agent on the top to this blue agent is going to be just 1. Okay? So it induces a metric cost. And this is the offline problem. So we are going to view each agent as a player, where the action of the player is to determine or to decide what resource to cache. Okay? And given that, we can associate a cost to that player, given an allocation profile P, which is going to be the sum of all the access costs, sum of the minimum of the access cost that player has to travel over the network to get access to all other resources. Okay. So the good thing is that this is going to induce a non-cooperative gain. And one can show that this is an ordinal potential gain. And the potential function is going to be a vector of sorted costs that every time that the player is going to best response and update its resource, the vector is going to drop lexicographically. Okay, so we can show that this is admits a pure Nash equilibrium. And the better news is that it has a price of anarchy of at most 3. So in other words, if we can find a Nash equilibrium here, we can approximate the optimal solution within a factor of 3. But the problem is, it's really hard to find the pure Nash equilibrium here. In fact, we conjecture that it's a PLS hard problem. We don't know how to find the pure Nash equilibrium. But instead, we design an online algorithm where when we follow the algorithm, the structure of the allocation profile, which is obtained at the end of the process, is going to mimic the same structure of the Nash equilibrium. And we pretty much get the same 3 approximation. And the algorithm is pretty simple. So every agent comes to the system. When agent I arrives to the system, we assign to its cache UI resources that have the furthest distance to that resource, to that agent. Okay? Very greedily, basically, each agent fills its cache given this cost function. And that gives this 3 competitive algorithm that I mentioned. So now getting back actually to Ashish's question, what about if we have installment cost, or we go beyond this metric cost, access cost? The situation here becomes much more complicated. In fact, we can think about a generalization of the problem where there are different request rates for different resources. So here in the previous example, I assume that the request rate for each resource is the same, is identical, okay? But what if we have different request rates for different resources. Unfortunately, the previous argument is not going to work here because one can show that the previous game that I defined here is not a potential game anymore. It doesn't have pure Nash equilibrium. But the question is, can we come up with a different game decomposition and mimic the same ideas to perhaps devise good algorithm? So in order to do that, we are going to look at the LP formulation of the problem. So this is exactly the integer program formulation of the data placement problem. SoCij's are the access cost. WJL is the request rate for resource L of agent J. And this FIL is the installment cost for caching resource L in agent I. Okay, so this is the installment cost that I mentioned earlier. And these constraints are basically saying that we shouldn't violate the cache constraints, and we have to make sure that each agent get access to every resource, and we can get access to a resource if that resource is already copied in cache of some agent. Okay, so these are the constraints that we have in the problem. Now, if you look at the dual formulation of this problem, where alpha I and beta JLs are the dual variables, and massage this dual formulation a little bit, we can cast it in this form, where you have a linear objective function with some piecewise convex constraints. Now, we are going to sum up all these dual constraints and guess the dual variable to beta JL to be this quantity, where DJPL is the minimum distance that agent J has to travel to get access to resource L given an allocation profile P. Okay? So this is the sum of the dual constraints that you see earlier with the difference that we are guessing the dual variable like this. So in this way, if you define the cost of the players like that, then this game again becomes a potential game, and it becomes an exact potential game. All right? So we are back to the business again, because now we can use the same idea that we had before. We get a pure Nash equilibrium here. If we get a pure Nash equilibrium, we basically want to minimize now the potential function of this game, where the potential function is going to be the global cost that we are basically trying to minimize. So yes?
What about the price hierarchy?
No, that doesn't hold here.
So we just want to convert to the...
Yes, exactly. So in this case, I mean, the best price of anarchy you can get is at most log n, because we have log n impossibilities, right? Right. Yeah. But the point is that we can now internalize the externality of the whole system to different agents and let them just selfishly update their resource. And if they do it in a nice way, we can still hit a global minimizer of this potential function, which is exactly what we are looking for. Good. So that basically suggests a type of Glauber type dynamics to find the Nash equilibrium here. So note that now the goal here is that we want these agents with this type of cost functions to update their resources, and we want them to converge to the best Nash equilibrium of this potential function. So this suggests this natural type of Glauber dynamics. At each time t, one player is going to wake up, and it's going to update its resource to some resource O with a probability which is proportional to the exponential terms of the cost function, the utility that you can obtain by caching resource O. Okay? So if a resource is bringing more benefit, we are going to most likely cache that resource. And with, of course, some noise parameter beta. And if you do this type of dynamics, then these dynamics are going to converge to some stationary distribution, which is given by the Gibbs distribution over all the allocation profiles that you could have in the game. So if the noise parameter is large, then we basically, all the mass of this probability distribution is going to concentrate around an allocation profile with the minimum potential value, and this is exactly what we are looking for. But of course, the price we have to pay here is the mixing time of these Glauber dynamics. So the higher beta we choose, the longer time it takes that these dynamics are going to mix to the stationary distribution. But still, for reasonably large values of beta, we can show that the dynamics are going to achieve a very good mixing time. So if beta is less than k, which is the number of resources, divided by 6 times c, where c is an upper cap for the cost function of the players, then one can show that these Glauber dynamics are going to mix in n log n iterations. So it's an interesting problem now. How can we push this idea to show fast mixing for higher values of beta? Because in that case, we can get a higher quality global minimum for the problem.
How bad is the best response dynamics?
It can be very bad, actually. If you just focus on finding a Nash equilibrium here, you are basically finding only a local minimum of this potential function, and one can show that local minimum of this function can be far away from the global minimum that we are looking for. Yeah. So we need this noise to get rid of this local minimum. Okay, so I think that basically concludes the first part of my talk. If there is any questions, please go ahead and ask. Otherwise, I will move on to the second part. Very good. So yeah, exactly. This handles the offline version of the general case, but we actually so if we go back to the online problem, in the previous case, we just let these players to greedily respond to their payoff function, their cost functions, by caching the right resources, right? So, and here we also have the cost functions. So we run this. We said, okay, let's try this idea that if each player comes to the system, is going to best respond to this cost function, and we simulated it, and surprisingly, it gives us very good competitive ratios. But we don't know any solid theoretical results to prove that. Yes, so that's an open problem. Yeah. Okay, great. So the second problem that I'm going to talk about is, again, an online optimization problem, where it's more related to online assortment problem. I'm pretty sure most of you are familiar with that. So if you go to an online platform such as Amazon or Airbnb and you search for some word like backpack, the platform is going to display a list of items where the buyer is going to choose one of them with some probability or decides to leave the market. And similarly, in Airbnb, when a customer searches for a room, based on the search data, the platform is going to display a list of available rooms, and you can either book it or decide not to book anything. Okay. So, but there is a difference between the amount of power that you give to an online platform. Sometimes the platform has full control over how to set the prices and how to match the supply and demand. And this is, for example, Uber is an example of this scenario, that it decides about how much to charge the passengers and how to match the supply and demand. Okay? But sometimes the platform just simply creates an environment for the trading, and the agents are going to interact there, and through their interactions, they're going to set the transaction prices, and the supply and demands are going to be matched in some way. Okay? And perhaps the Airbnb would be one example of this type of platforms, where the price of the houses is going to be set by the individual hosts rather than the platform. So again, there is a large literature on online assortment problems. So there are very beautiful work by Negin Golrezai, who was here today and yesterday, work by Amin Saberi and Rod. Actually, they also work on extension of these online assortment problems for reusable resources. And this idea has been extended to different versions of this online assortment problem with different constraints. But what I'm going to actually talk today is a competitive version of online assortment problems, where you want to solve this assortment problem subject to the fact that there is a competition among sellers or buyers in the system. And we want to see how would these results extend to these more competitive scenarios. Okay? So perhaps this work is very related also to a recent work of Shrikant and Zhang, that they consider basically the static version of the problem that I'm going to explain soon. So there's a very beautiful result that basically they show that they can, for the static problem, they can solve they can find the optimal assortment given that you have some structure in the problem. So here is the formulation that I'm going to talk in the next few minutes. So again, we consider a set of n sellers. Each of them is holding one item. So I'm going to use seller and item interchangeably. Okay? And we assume that seller I has Ci units of item I, where this is a private information to seller I. And moreover, we assume that each item has a fixed quality. We denote the quality of item I by a real number, which can be either positive or negative. If it's negative, it means that a buyer prefers to leave the market rather than buying that item because the item has negative quality. Okay? So an unknown number of buyers are going to sequentially join the platform. And when a buyer comes, and assuming that we post some prices P1 up to Pn on the items, we assume that the buyer is going to buy that item with a probability which is given by this standard multinomial logic choice model, which basically is increasing as a quality of the items, but decreasing in terms of the price. Okay? So the higher quality the item has, the more likely the buyer is going to buy it. But of course, it also depends on the price. If you put higher price, sometimes the buyer decides not to buy it. Okay? So that's the choice model that we consider here. And now at time t, what happens is that the platform offers an assortment ST, and it's going to induce a competition among the sellers in that assortment. So let's say the platform offers a set of ST of the sellers. Then the sellers are going to get into a Bertrand competition and determine what prices to choose for their items. Okay, so basically you offer a set of sellers in set ST. There is one buyer, and then it induces a Bertrand competition. The sellers are going to determine their equilibrium prices, which is given by this expression on the bottom of the page, which is proportional to 1 over 1 minus the probability that item I is getting sold. And therefore, the revenue that we get from item I, if we include it into the assortment, is going to be given by the probability that item is being sold times the price, which is 1 over 1 minus Qi. So this is the revenue that we get from item I if we include it at time t in the assortment ST. Otherwise, we don't get anything out of it. Okay? And the platform's goal is to come up with a sequence of assortments which respect the inventory constraints that we have. And we want to maximize the overall revenue that you can extract from all these items, all these sellers over the horizon. Okay? So that's the online assortment problem. And here is a simple example which illustrates this idea. Suppose we have 4 items. The first one has 4 units. The second has 3 units, etc. And the last one that you see here is the no purchase item. If the seller buys this item, it means it's just deciding to leave the market rather than buying anything. Okay? So the first buyer comes to the market. Let's say the platform is going to offer this assortment. Then these sellers are going to get into a Bertrand competition. They're going to compute their equilibrium prices. Depending on these prices, the buyer is going to select one of them based on multinomial logic choice model. Let's say it chooses the red item, and then the next buyer comes, we offer a new assortment, equilibrium prices are computed, and so on and so forth. Okay? So for example, in this case, in the last case, if we offer the assortment ST, which only includes the yellow item, then since there is no competition here, probably the seller, the yellow seller is going to set a higher price for its item, which basically disincentivizes the buyer to buy that item, and therefore it prefers to leave the market rather than purchasing that item. So as you can see, the crucial part here is that the prices are functions of the assortments that you are offering. Okay, it's not fixed anymore over time. And that creates extra externality among these sellers. So now the question, a few quick remarks about the information structure of the problem. So we are interested in either deterministic or online algorithms to come up with good competitive ratio for this problem. And by online algorithm, I'm referring to the scenario that we don't know the number of the buyers and we don't know the inventory levels a priori. And we want to compete against the best clairvoyant online algorithm. Best clairvoyant online algorithm is an algorithm which basically knows the total number of buyers. It knows the current state of the inventory and everything that has happened in the past, but it has no information about the realization, the choice realization of the buyers in the future. Okay, so we are going to compete against the best clairvoyant algorithm. And again, we are going to use competitive ratio to measure the performance of our algorithm. How close we can get into this best clairvoyant. Sure. The theta parameters, yes. Yeah. Yeah. The qualities are known and can assume they are. Very good question. So exactly. So if we don't know these qualities, I'll show you soon that there is no competitive algorithm for the problem. Yeah. So we have to move to the scenario that this information is public.
And then another question about the offline version. What do we know about this new revenue function?
Right. Yes, that's exactly the problem which was studied by Shrika and others. In that case, yeah, the optimal assortment for one-shot game is going to, I think if I remember correctly, you need to sort these items based on their qualities. And the optimal assortment is a chunk of these items from the highest quality to some level. But with a brute force search, you can figure out what is the... Yeah. So that is for the static version, yeah, the problem. Yeah. Great. So here, getting back actually to your question, if we assume that buyers have different evaluations for the items, meaning that this, let's say buyer T has evaluation theta 1T for the first item and etc. for other buyers, then in that case, there is no constant competitive algorithm for the problem. But soon we move to homogeneous case when this quality of the items are publicly known, so all the buyers have the same evaluations about the items. Then a simple deterministic algorithm again gives a constant competitive ratio. And this is how the algorithm works, basically. It's a simple threshold-based policy. So we are going to set a threshold lambda, and we are going to divide the items to two groups. Any item that once you offer it individually is going to attract the buyer by a probability of at least lambda is going to be called the heavy item. These are high-quality items that we have in the inventory. Okay? And anything other than that, we call them light items. So these are basically the low-quality items that it's hard to sell them to the buyer. And then we have to go through this two-phase algorithm. So we are going to sort the heavy items based on their heaviness level, where the heaviness, as I said, is the demand that you have for the item, given that you offer it individually. Okay? This can be computed a priori by the platform. So a simple calculation can compute that. And then starting from time t, we are going to offer the items in this list one by one and individually to the buyer until either we run out of heavy items, no heavy item is left, or we run out of buyers. If we run out of heavy items, but there are still more buyers coming to the market, then we are going to bundle all the remaining light items together and then offer it to the buyer. Okay? So it's a two-phase algorithm. And the idea is that when an item has high quality, very likely the customer is going to buy it with high probability. So we shouldn't really sacrifice the price of that item because you can sell it at a high price. But when you are dealing with light items, the problem here is that we are going to lose our customers. So we are going to offer all the light items together in order to have higher demand rate for in order to make sure that we are trapping the customers in the system. Okay? And if now we optimize through the threshold policy and do the math, one can show that for this parameter lambda equals 0.63, the algorithm achieves the constant competitive ratio. The competitive ratio is very low, but our goal was to first come up with the constant competitive algorithm, and it's a good question: how can we push this competitive ratio higher than what it is? So we did not really optimize over all the parameters because it's kind of and the running time is polynomial in terms of the number of buyers and the number of sellers.
Know the number of buyers and the capacity.
If you know the number of buyers and what else?
And capacity. So the optimal offline.
Oh, and in that case, they don't have a simple characterization. If different items have different inventory levels, and you're looking at the one-shot.
Optimal offline. So you have multiple buyers.
I see.
Homogeneous.
Okay. There is no simple structure, I think, as far as I know. Yeah.
But still, your algorithm is kind of giving a threshold on the quality.
Yes. Okay. Okay, great. So I don't know if I have enough time, maybe, to quickly comment on the idea. Okay, great. So let me quickly talk about some of the ideas behind the proof. So the first part of the proof is pretty straightforward. It has been used widely in the past literature. What we are going to do, we are going to write a linear program with exponentially many variables, which is going to upper bound the cost of the revenue of the optimal clairvoyant online algorithm. And we are going to design our algorithm to be competitive with this optimal value. Okay? So a typical approach here is that in order to design a good online algorithm, we have to look at the dual of this linear program and design our algorithm such that the algorithm is going to generate a primal solution to this linear program. And we are going to guess the dual variables using some dual fitting techniques and show that the cost of the algorithm is going to be within some constant factor of the cost of the dual, and using some weak duality that shows basically establishes the competitive ratio. Unfortunately, here the situation is more complicated, and because the price of the items, as I said, are assortment dependent. So guessing these dual variables are going to be very difficult, or at least we couldn't come up with any way to guess these dual variables. So instead, we attacked the primal problem directly, and using the two-stage algorithm that I described, we are going to fill these primal variables over the trajectories of the algorithm. Okay, so we run this algorithm, and based on how it generates these assortments and how much the prices are going to be set, we are going to fill this large scale LP using some charging arguments. And more precisely, we show that if for all sample paths that the algorithm has a chance to get into its second phase, the expected revenue that we get from phase 2 is within a constant factor of the expected revenue that the light items are going to contribute to this optimal solution here. And moreover, if the algorithm doesn't get a chance to enter its second phase, the revenue that we obtain from selling heavy items is reasonably large enough to be still competitive with the optimal value that we have here. And putting these two pieces together, we get kind of a complicated relation based on the parameters of all the problem, all the parameters we have in the problem, and we do some optimization to come up with that constant competitive ratio that I mentioned. Okay. All right, great. So that basically concludes my talk about the second problem. And to have a quick conclusion, we consider two types of online platforms here that they exhibit high levels of externalities. The externality in the first problem comes from the congestion of the resources as more agents are joining to the system. For the second problem, the externalities come from the competition among the sellers in the offered assortments. So the problem is when we look at the adversarial setting, in both problems we saw that it's really hard to come up with competitive algorithms. So either we don't have constant competitive algorithms or at best like logarithmic or something. But soon we move to homogeneous setting, there are actually some constant competitive algorithms. So the question is, how can we design some algorithms which are on sweet spot, somewhere in between? And to do so, we need to relax some of these hard constraints on their problem. So one way of doing it is perhaps to look into some underlying information structure that we might have in the problem. And as the platform is interacting with the agents, we try to learn some important information and try to design our algorithm to incorporate that information in order to get better constant competitive algorithms. So there are actually some interesting works one can think about it. So here, how can we extend our results to more general settings? So for example, I only assume multinomial logic choice model. What if we work with more general choice models like Markov choice models? And how can we, so for example, in the online resource allocation problem, one interesting question is that as more agents are coming to the system, by interacting with the agents, you can perhaps learn their demand rates or their request rates, and then use that information to design a better online algorithm. Okay. So with that, I would like to conclude my talk, and thanks very much for your attention.
There's time for questions before the
I have a question. Like two aspects there here when you showed the configuration of the
Yes.
Yeah. So, do you have a capacity constraint on the? So, do you have a capacity constraint on the total number of products, or does each product have a separate capacity constraint?
Each product has a separate. So here C is a vector of the inventory
so Q
levels.
is vector,
So,
C is, okay, good.
This is written in a vector form, compact.
Gotcha.
Yeah, good question.
All right, thanks.
Okay.
that's fine.
Thank you.